I'm going to briefly talk about some of the stuff we've covered already, real quick, and then I'm going to go into conservation of energy, and then from there we'll talk about a little bit about power and what power is, and how we calculate power. So in the past we've done a bunch of stuff. We started out talking about work, and I know that we've done this recap before, but just so everybody's on the same page, let's do it one more time. At the beginning we talked about work, and we said work had an equation, which is work is equal to force times displacement or distance times cosine of theta. Theta is the angle between the force vector and the distance vector d. We also talked about energy and the three different types of energy. There was a kinetic energy, 1/2 mv squared. There's a potential energy, UG, which is due to gravity, which we will call mgy. And then we have a spring energy, U sub s is equal to 1/2 kx squared, where k is that spring constant, x is this distance that the spring's been stretched from its natural equilibrium length. The next thing we did was we put those things together, and we created this thing called the total mechanical energy. And I'll do that in blue. So we said E is our total mechanical energy, and it is equal to T plus UG plus US, and that's the total mechanical energy. We add all of the energies together, and that's how we get it. Then we also talked about this conservation of energy, and conservation of energy happens when we have no non-conservative forces acting, and all the forces that are acting are from inside of our system. So if I have a spring and a mass and it's oscillating on a frictionless surface, if I say the spring and the mass are my system, and I don't have to include the earth in this one because there's no like if I draw a picture, here's my spring and mass system. If I say that this position here is y is equal to 0, it'll always be 0, and so mgy will always be 0. And so the only energies I'm going to have is my spring and my force. So I won't need to include earth on this, just the spring and the mass. And then all the energies involved are going to be a kinetic energy, 1/2 mv squared, and a potential energy due to the spring. If the spring is part of my system, everything is internal to the system. All the forces are exerted inside of the system, and it will cause a change of energy inside of the system. And that's why we'd say this is a conservative system. No non-conservative forces, because there's no friction, but also all the forces that are acting are within our system. Another situation we can have is a ball. Maybe it's going to fall or be thrown up in the air or thrown down from the height of a building or something. If we consider the ball and the earth to be our system, then there is no external forces acting on it. So the gravity force is part of this earth ball system, and that is internal to the system, and it is a conservative force. And since we don't also deal with drag forces, there's no air resistance, nothing like that. There's no dissipative or non-conservative forces. That means that this whole situation here for our ball falling, if we consider the ball and the earth, has no external forces, just the internal gravity force. And so that would also be a conservative system. So when we have a conservative system, we can do problems with it, and we use the equation delta E is equal to 0. That is, the change in the total mechanical energy is equal to 0. Another way of saying that is E final equals E initial. E final equals E initial. That's pretty much where we start off with most of these problems. We would set up something, maybe a part of this problem. Ooh, wow. We would start off maybe here at some x initial, and it would go to some x final. Maybe that x final is where the spring is not stretched anymore, so it's not exerting any force. We would know that at the initial position, that would be the maximum distance it will ever reach. And when we start, maybe we stretched it out and we'll just let it go. It'll start from rest, and our initial velocity will be 0. Then at the middle point, our final position is going to be 0, and our velocity V final will be the maximum velocity. And so we can set up a conservation of energy that would say that the T final, which is our final kinetic energy, and since there's no spring energy at that final position, just T final is equal to U sub S initial, because there's no velocity at the beginning. V is 0, so 1/2 mv squared is also 0. Therefore, the only energy in that system at the beginning is spring. And then we can do some stuff. We can maybe solve for a constant or a stretch distance or a velocity, maximum velocity, something like that. And then we could plug it into like another position on this motion. And I will give you some examples for that. Well, a example of that. Okay, so the big takeaway from this part, though, is E final is equal to E initial. Now, let's say that I wanted to do a problem like that. Well, I'd have to plug into my E final. My E final would include a kinetic energy final plus a potential gravity final plus a potential spring final, and that would be equal to my initial stuff, which would be a T initial plus UG initial plus US initial. And we said that y is 0, and we're talking about the spring situation here. So y is 0, which means my gravity initial is going to be 0. Also, my gravity final will be 0 because they are both on that same y level, right? It hasn't gone up or down, and so there's been no difference in kinetic, or no difference in gravity potential energy, and that's what we're talking about, right? This is delta E, and so if I subtract out this 1/2 mv, or sorry, this mgy from both sides, it goes away, even if it's not 0. Right? So if I'm maybe some distance h above the ground and I'm oscillating back and forth horizontally, that's not going to affect my motion, because when I talk about anything that I'm trying to solve problems for or something like that, I have to use something like conservation of energy or the work energy theorem. And the work energy theorem has that change in position in it for gravity. So my UGY in my delta E, let me write that over here, delta E will have a delta T in it for a change in kinetic energy, plus a change in spring energy if there is a spring, plus a change in gravity. So this gravity energy change would be not 1/2, it would be just mgy final minus mgy initial. And if it's staying at that same value of y the entire time, those two terms are going to be equal to each other. They're subtracted and they go to 0. So we can say UG initial is going to be 0 as well as UG final. But then our T initial, if we're going to release this thing from rest, our T initial is going to also be 0 because our velocity initial is 0. And there's one more thing that would go to 0, and that's our spring energy. That's going to be 0 because X final is 0. What we are left with then is just a T final is equal to US initial, and then from here we can plug in some equations, which are 1/2 mv final squared is equal to it is equal to 1/2 kx initial squared. I can multiply both sides by 2, I would get some equation, and I could maybe solve for some unknown, something I didn't know. Sometimes you'll be asked about a point somewhere else in this motion, and then you'll use some of this information that you've gained from taking your mv final squared is equal to kx initial squared equation and solving for it. You'll see that here shortly. So the last thing that we talked about with energy was that conservation of energy. And the conservation of energy is really a special case of a bigger thing. And that bigger thing is what we call the work energy theorem, which we'll give number 5. And I've gone through this, I'm pretty sure, for every class, but just to make sure that I'm not missing any points. We said that our work total, which I'll just call capital W, is equal to the work done by forces, right? So there are 2 broad categories of forces. Those are the non-conservative forces and the conservative forces, and each one will do some kind of work on the system. When we talk about a conservative force, we saw that the delta E is going to change, but it's always going to be internally. And so overall, the energy of the system doesn't change. The total energy of the system doesn't change, but the individual pieces will change. And this is kind of like when maybe if you took chemistry, you might remember this equation, PV equals nRT. And let's say that we wanted to know something about P and V. So we could say P initial, V initial is equal to nRT, which has to also equal to P final times V final. And then we could solve this equation, say P initial, V initial is equal to P final, V final, and maybe solve for our final velocity, which is P initial, V initial over P final. If you remember this was one of our laws. It is part of the ideal gas law for sure, but there was another law for it. Let's see, it was called, I think that was called Boyle's law. So V final is equal to P initial, V initial over P final. And this works because we have this thing here, P initial times V initial, and this thing here, P final times V final. because they are equal to the same thing, nRT. And this, maybe you didn't hear about this in chemistry, but the real thing that happens is that we're not losing a number of particles in this situation, and we're not changing the temperature. And because those are constant, this whole thing in that red box is also constant. And so if P changes, then V also has to change to keep that constant the same number. If P were to change and V didn't change, then it would no longer be equal to nRT, and this whole situation falls apart and we can't use it. In a similar fashion, that's what's going to happen with our work done by conservative forces. That is, the work will be done by conservative force, and what it will do is it will cause a change in like a spring energy, which will also be equal to the same change in the gravity energy. So if I change my spring energy by 1 joule, maybe I reduce it by 1 joule because it's, you know, getting closer to that natural equilibrium point. It's pulling that mass in towards the zero. That means that the other energies or kinetic energy has to change to make up for that. And so this is a pretty simple thing, but it turns out that our work due to conservative forces will cause a change in just our 2 potential energies, because these are associated with a potential energy, right? Every time that we have a force that is path independent and internal to the system, it will be a conservative force, and it will cause an energy to happen. So the 2 forces that we dealt with are our spring force, and so our work due to a conservative force can cause a change in our spring force, and the other conservative force was gravity. And so work done by one of these conservative forces could cause a change in gravity energy, or it could cause a change in the spring energy. Maybe you saw that at one point in some lab where you hung a spring on a rod or something, and then you hung a mass at the bottom of the spring and it stretched out until it stopped stretching. What happened there was you converted some of the gravity potential energy into spring potential energy when you stretched that spring out. And this is basically done by a conservative force, and all the forces acting to balance each other out to cause a zero acceleration are all conservative forces. And so work done by conservative forces causes delta U sub S plus delta U sub G. I'm going to put that aside, and we're going to talk about the other piece, and that is the work done by non-conservative forces. Circle that in red. The work done by a non-conservative force, I kind of hinted at this in the class at one point or another, but if you have friction, it will cause a change in velocity, right? It will reduce your velocity. Drag force will reduce your velocity. If I push on an object, I could increase its velocity. If I pull on an object, I could increase it, maybe even decrease it. I could push on an object and decrease its velocity too. But the point is that the work that these non-conservative forces do, it causes some kind of change in energy. And it turns out that that is 1/2 mv squared final minus 1/2 mv squared initial, or delta T. Work due to non-conservative forces is equal to change in kinetic energy. This is our work kinetic energy theorem. And it is a really good starting point for the work energy theorem. The work kinetic energy theorem says non-conservative forces, these outside forces that are not path independent, that do depend on a path that they take, they will cause a change in kinetic energy, and only kinetic energy. So let's look at some of these forces that could happen. And first of all, let's talk about the actual conservative forces, and then we'll talk about non-conservative forces. So here I am at y initial, and eventually, you know, this table or a building or something. Down here is y final, and if I drop this ball, it's going to go all the way down, and it's going to hit that bottom point. And the change in gravity energy is going to be mg times y final minus y initial. So I just set up mg y final minus mg y initial. I factor out mg, and this is what I get. And that's delta ug, right? But it doesn't matter if I drop the ball or if I throw it directly up. It'll come back down, it'll do the same motion, and ultimately it'll have the same change in energy, because this displacement here doesn't affect things because of our path independence. But also if I threw it at an angle, and so it did like an arcing motion, that motion on this part is going to go up and back down, and it is path independent. So those two things will cancel out, just like our displacement says. If we take, if we just consider that first part of the motion where it goes up from y initial to some maximum value and then back down to y initial, the overall displacement there is 0, and so that has no effect on the gravity. But it's going to fall all the way back down, and then there will be this change in gravity, or this change in position, that is not, it doesn't go back up, right? So it's not canceled out in that displacement equation or calculation. And so what we have is a overall change in energy due to this ball falling from y initial to y final. It doesn't matter how it falls from y initial to y final, it'll always be the same energy. All three of these scenarios I drew, whether I'm dropping the ball, whether I'm throwing it down, whether I'm throwing it directly up, or whether I'm throwing it up at an angle, all three of them will have, or all four of those scenarios, they will have the same change in gravity potential energy. Now, they might not have the same total energy. If I throw it down with a certain velocity, that gives it initial kinetic energy, and that'll be different from dropping it. But the change in gravity energy only will be the same. And so these forces, gravity force does not depend on the position. And I also said something about our spring force, right? If I have a spring and I pull it out some distance, so here's my x initial, here's my x equals 0 point. I pull it out, its velocity is 0, I let it go. It takes that that stored energy in the spring, and it pulls that mass to the left. It'll pass through the 0 point. When it passes through the 0 point, it has the maximum velocity and 0 gravity energy, and then it'll keep oscillating back and forth. But if I look at this point right here, maybe we'll call it like x sub 2. If I look at this point right here, it doesn't matter how many times I've oscillated back and forth, again, assuming that this is a frictionless surface, it won't matter how many times I oscillate back and forth, because it'll just keep going back and forth over and over again. And every time it hits that x2 position, it's always going to have the same magnitude of velocity. It's always going to be at the same stretch distance. The spring constant is going to be the same, and m is going to be the same. And so there is going to be no difference between making 0 oscillations, whether it just went from x initial to x2, whether it makes one oscillation, so it went from x initial all the way compressed back to x initial and then back to x2, or it could do it like a billion times. It doesn't matter. The difference is unimportant, right? The problem will be the same as if it had just gone from x initial to x2. And so that is what we call path independence. But then there's these non-conservative forces, which are not path independent. So here is a starting position, and here's an ending position. And we know the shortest distance between these 2 points is that straight line. And if I push a force on a friction surface, friction will do a certain amount of work sub F for friction. But that work done by friction here, and we'll call it WF1, is going to be less than the work done by friction if I do this path. We'll call WF2. And if I were to go this way and just circle around, maybe making concentric circles and going curly Q, this work here, work 3, that is going to be more than those other two combined, right? And so forces like friction and drag, they are not path independent for this reason. So they will still change the velocity. That friction force will still change our velocity, but it will not change our potential energies. So what we get then is our work due to non-conservative forces equal to delta T, and then we have a work due to conservative forces, which is delta US plus delta UG. Work due to non-conservative forces, we can just pretty much add these two things together, right? I say work due to non-conservative force plus work due to the conservative forces. Well, we said that was equal to the total work, but it's also equal to a delta T plus delta US plus delta UG, and it will give you basically delta E. And so delta E is equal to the total work done. So change in energy is equal to the total work done by all forces, not just conservative or non-conservative forces, but the work done by all forces causes a change in total mechanical energy. This is our work energy theorem. The next thing that we need to do is realize that if there is no net work done, right? If all of our forces add together and sum to 0, then work will be 0. And what we get is delta E is equal to 0 for no net work done. And that delta E equals 0 is our conservation of energy statement. So this conservation of energy thing is a special case of the work energy theorem. And that's a really important case to make. So we can now say something like work, which is force times distance times cosine theta, is equal to 1/2 mv. Let me go back. 1/2 m times v final squared minus v initial squared. So it's just 1/2 m delta v squared. Sorry, 1/2 m delta v squared. Plus 1/2 k times x final squared minus x initial squared plus mg times y final minus y initial. And that is our statement of the work energy theorem that we can really get into and use. So we'll do some practice problems with that. Might have to wait until Monday to do it, but we'll go through a bunch of problems and get ready for the summative starting on Monday and Tuesday. Okay, so last thing that I really want to hit hard is this power thing. I kind of talked about it a little bit at the beginning, but power is a special thing. Just like energy, just like work, we have a lot of ways to describe what power is, but in physics, it is a special thing. And we say that power is actually the work done over some amount of time. So work is equal to, it is work over time, and that's what we're going to call our power. But power or work, we know through the work energy theorem, is also equal to a change in energy. That means that our power is delta E over T or W over T. So work is done by some forces, some net force, and then if we divide that by the time that the forces act, then we will have a power. So we said that work is force times displacement times cosine theta. Cosine theta doesn't have units. Force has units of newtons. Displacement has units of meters. A newtons times a meter, we call that a joule. Same thing with energy. We'd have a 1/2 an m and a v squared. That would be a kilogram times a meter squared over a second squared, which is a newton times a meter or a joule. For our potential energy for gravity, we'd have mgy, which is kilograms for mass times gravity, which is an acceleration, meters per second squared. That's a newton, times y, which is a meter. So we'd have newtons times meters or joules. The last one, we have 1/2 kx squared, which 1/2 doesn't have units, but k has units of newtons per meter, and x has units of meters squared. So when I cancel out one of those meters in the squared with the meter down below from k, I would get newtons times meters, also a joule. So all of these have had units of joules. That means delta E and W both have units of joules. And so power has units of joules over time, but time is in seconds. So to do this unit, we will give it a special name as well. We call that unit the watt, and we abbreviate it with W for watt. I know that this W is a unit, not work, right? So be very careful when we talk about units versus symbols to represent our quantities like work. There's another thing that we did earlier with like the square root of k over m, where we have m is mass here, and so mass would be in kilograms. But also in k's units are newtons per meter, and so we'd have a meter there. So be careful, because a similar thing will happen with those lowercase m's and these w's for watts versus work. So just be aware that that's a mistake you might accidentally make. Anyway, so if we take our power equation, which says power is equal to delta E over T, or maybe let's call it W over T. I know my equation for work. That is F times D times cosine theta over T. And then what I'm going to do is I'm going to move some stuff around. I'm going to say that my FD cosine theta, I'm going to call it F cosine theta times d over t. If you remember from unit 1, distance over time, that's what we called our velocity. So if we do F times our velocity, F cosine theta times our velocity, and let's just go ahead and make the assumption that these things are going to be acting horizontally, so cosine theta will be 1 or minus 1. We'll just say it's F times V then. So our work we can also calculate as being F times V, force times the velocity. If we want to talk about the change, we can talk about F times delta V as well. So the watt itself as a unit is made up of joules and seconds, but another unit of work that you've probably heard about quite a few times is the horsepower. And this horsepower thing is created by the same guy who created basically work and the equations for work, or found the equations for work. And this, what the guy who this work stuff is named after, or the units of work is named after, is James Watt. He invented, well, he didn't really invent, but he made some significant improvements on the original steam engine, which was invented by, I think it was like Thomas Newcomen or something like that, some engineer back in England. And James Watt introduced a condensing cylinder, and it was able to run the steam engine at much lower temperatures. It was much more efficient, and it could do the work of lots and lots of horses. And he also invented, I think he invented methods for like sealing pistons and making gaskets and stuff to minimize energy loss due to leakage, all kinds of things that he did. But anyways, he invented this thing, or these improvements for the steam engine, and they had to market it to people, and people were not familiar with engines at the time, but they were familiar with the work that horses could do, and so he called this thing a horsepower, and a horsepower is equal to 746 watts. The reason why he came up with this idea is because he wanted to just kind of relate his new engine to the work that a team of horses could do. And said, a team of horses, they have to stop, they have to eat, you have to feed them, you have to house them, you can't run them at night. This engine thing that I've improved upon significantly, it doesn't need any of that stuff, and it can work continuously all day, all night. All you have to do is have it running. And so that's like the equivalent of 746 horses, something like that. But without Watts' improvements to the steam engine, the Industrial Revolution probably wouldn't have happened. And this was, again, just a marketing tool, really, more than anything. It didn't really represent much of anything until we started to really do these calculations with energy and work and stuff, and people got into it. So if we want to talk about maybe a problem, let's say that we have a force. Let's say we have a motor, and we want to lift that. We want to use that motor to lift a 300 kilogram object up a distance of 10 meters, and we want to do this every minute. Or maybe not 300 kilograms of an object. Let's say it's a water, and we're doing a water pump. We want to move 300 kilograms of water every minute up a distance of 10 meters. And that's a lot of what the original applications of the steam engine were to drain mines and stuff like that, so they could get it at like peat moss, so they could get at coal, precious metals, things like that, or useful metals like iron and tin and stuff. So they would drain this stuff out, and let's do a calculation to see what kind of power our engine would need to be rated at to come up with, to perform this task. So our power is equal to work over time, and that work is going to be the work done by the engine. So the engine is what's actually doing this work, and we can calculate that as force times distance times cosine theta over time. If I think about it, here's my hose, it's going to go up and out, and this distance here without the curve in it is that 10 meters. So what am I going to be doing for this water? Well, I'm going to be working against gravity. So this force right here, that's going to be a force of gravity on the water pulling it down, and our force that the engine has to exert must be at least equal to that. So force of gravity is going to be mg times d times cosine theta, all over that time. Now my displacement is up, and my force that my, put D there, the force that my engine is going to exert is also going to be up, which will counteract and be equal to gravity. So that tells me that my cosine theta, well, that's going to be 1, because theta here, as you can see from these two vectors, theta is 0 degrees. So cosine of 0 is 1. I can just plug in some numbers. I would put in my mass, which is the 300 kilograms of water we want to move. Our gravity constant is 10 meters per second squared. Displacement will be 10 meters. And then we're going to divide by 10 minutes. But we don't use minutes in physics, we use seconds. And so we need to multiply this by 60. And so we divide it by 600 seconds instead of 10 minutes. If I plug that into my calculator, it should be somewhere around 50 watts, if I did that correctly. But yeah, that is our calculation for how we do work. Obviously, if we wanted to like change the velocity, do work to change the velocity of a car, we use like 1/2 mv squared final minus 1/2 mv squared initial over time. Or if we want to do work to extend a spring some distance, we could use 1/2 kx final squared over minus 1/2 k initial squared over time. Any force that we have that has an energy with it or changes the kinetic energy, we can just put that in on top and divide it by the time that it takes to do it, and that will give us our power amount. So that is power. Let's do one more quick example of power. That is P is equal to the force times velocity. So we had two ways of calculating power: work over time or force times velocity. So if I do let's say I want to start a car from rest and accelerate it to 30 meters per second. And I knew that the force I was going to exert was maybe, say, 904.8 newtons. That's the force my engine will exert on the object. And then I have a velocity that I'm trying to reach, which is 30 meters per second. So all I have to do is take those two numbers, F times V, which would be 904.8 newtons times 30 meters per second. And I would get 27,144 watts. That would be my answer. That's my power rating for my engine for that. All right, that's all I really wanted to talk about. This pretty much finishes up our unit. Unit number 3, we'll do some examples. I will maybe post a ed puzzle or something for you guys to work on over the weekend, and then we can get back together from there. So good luck.